Um, I'd like to talk a little bit about why it is that I ramble on about quantum consensus, just in terms of common sense. Um, and so I'd like to begin with just checking in and see who here is familiar with the EPR experiments or the Bell inequalities. Just in general, the whole spooky action at a distance aspect of quantum mechanics. Like if someone were to ask you, you were out and about and you were maybe waiting on a bus or something or in a pub, and someone said, well, hey, can you explain to me what that's all about? Who here could explain, just in layman's terms, what's going on there?
I was just this weekend playing with quantum stuff on IBM site. So it's fresh to me.
All right. Well, you want to give it a go? You want to explain to us what just in layman's terms what's going on?
So my understanding is the Bell state means that two qubits are entangled, and
yes, that's right.
So basically, the entanglement also means when we do the measurement, we are basically entangling the qubit with our state, which because our state is not in any superposition, this means that entanglement will be like connected to our state, which means the superposition will be destroyed. And so because I was interested in quantum teleportation, so what this means. And so my understanding is that we first want to isolate these qubits so that we can entangle two qubits together, but they are isolated for anything else, from everything else. And then yes, we can also entangle some additional qubits that we want to send. And then we are basically doing the measurement yeah, so my understanding is that we first want to create so we are creating superposition of our qubits that we want to send.
House, at least for now.
Sorry?
Rao?
Yeah, I'm in.
Okay. Okay. Go ahead, Tomislav.
Yeah, I'm not sure what exactly I want to say, but this is my understanding is now that the Bell state is basically the entanglement, and the measurement also means entangling the qubits to something.
Yeah, but the important thing is that once you have two states that are entangled, then you get correlations on observables, and that's the thing that so like if you're explaining to someone the idea to someone in a pub, if you just said entanglement, they're not necessarily going to know what that means. But the important thing is that once two states are entangled, then there are some observables that become correlated. So, for example, the spin of one particle becomes correlated with the spin of another particle. And the reason that's important is, or the reason that that's weird or noteworthy is because it doesn't matter how far apart your two particles are physically. And as a result, you know, I mean, this is the thing that was troubling to Einstein. You know, it looks, you know, it looks as though you get this superluminal communication because instantly, whatever you measure in one location, you will know the value of that observable for the other entangled state in the other location. That's the thing that was troubling to Einstein and makes people feel a bit strange. Now the reason, so I just want to stop there and make sure that that's clear to folks. That you don't have to know much about entanglement, the math of it, but the main point is that if you have two states that are entangled, then there will be some observable or observables such that you get statistical correlations, so that if you measure this observable for one state, for the other state, you will see that the observable is correlated, no matter how far apart these particles are.
And when you say observable, is this means
Like the spin of a particle.
So this is the measurement operation. So one qubit is one observable, or we can have different.
Yeah, a qubit is an observable. Yeah.
Yeah,
Oh.
I get the idea of quantum entanglement, right?
Yes. So now, like, what is going on if we then think about Casper? The question that we want to ask is, what's happening in Casper? What is Casper affecting? Well, the observable in this case is the winner of a given race. So you have an observable, which is that you've got two inputs and one output, and that can only have one of two outcomes. So if I have input on, the input goes to the left side of the race, or the input, so the output goes to the left side of the race, or it goes to the right side of the race, one or the other. And with Casper, we know that if we observe at one validator the winner of the race, then if Casper is doing its job, we know the winner of the race at another validator, no matter how far apart the validators are on planet Earth. Right? That's the whole point of Casper, is to do exactly that, is to make sure that if we're sitting at one validator and we observe the winner of the race, then we know what the validator is, what some other validator will observe with respect to that particular observable. Does that make sense?
Yep.
Yes.
So this is why I have long said that the quantum mechanics provides an interesting, it seems to provide an interesting mechanism for consensus, right? The entanglement would seem to offer exactly what we need in terms of consensus, because what it does is it gives us correlation on some observables. And the interesting thing is that we could have a layer of abstraction. We could say that for any state where I have n races, I need n qubits, and a validator just simply measures and knows how the race has to be, and how to assign the winners of the race. And so as long as the validators are able to have the appropriate and entangled states, right? If you could pass out the states ahead of time, then the validators could all just check the observables for those states and know how to assign the winners of the race. And every validator would be able to make with the right setup up front, every validator would know exactly how to assign the winners of the race. So that's the basic idea, and it's relatively straightforward, relatively simple and clear. And we can one of the interesting things is that well, there's several interesting things. We could therefore view the implementation of Casper that we have today as a classical simulation of quantum. So that's one thing that's interesting. Like, to what extent does the existing Casper protocol represent a classical version, a classical simulation of a certain aspect of quantum mechanics? And we can that's something that we could check mathematically. We could check, does Casper satisfy certain requirements? So if you go and you look at Bob Cook's book, Picturing Quantum Processes, he gives an axiomatic characterization of these systems and shows that that this is a fairly abstract characterization, so that you can get it's like for example, as long as you have a complex closed category, you have enough machinery to realize a lot of what we understand to be quantum, and then shows that, for example, the category of sets and relations, as opposed to sets and functions, is compact closed. And so you can get a lot of what we think of as quantum teleportation can be realized in the category of sets and relations. And so you can, but we know how to implement sets and relations, right? That's something you can do in Scala. So there's a sense in which we could check to see whether or not what we've implemented with Casper gives us, some portion of the axiomatic requirements for implementing protocols like quantum teleportation, even though we don't have the instantaneous nature that we see in existing quantum mechanics, like with physical systems. And of course, because of that, we can imagine flipping the script and saying, well, can I therefore use quantum mechanics to implement Casper? So that's why I have been, you know, so interested in and convinced that there's something about quantum mechanics that would be a very good fit for what we're trying to do with Casper. And moreover, that it provides a kind of correctness criteria. So, you know, what we know at least with respect to Roland, what it is we want Casper to do. And that thing that we want Casper to do lines up very naturally and very nicely with what we can get quantum systems to do. And so it's at least conceivable that we could take some of the specifications of what quantum systems do and massage them into a spec for Casper, you know, a high level spec says, you know, so that we get an axiomatic presentation of what Casper should do in terms of, say, the graphical calculus that that Bob and others have developed. So let me just stop there and see if what I'm saying makes sense.
So you're saying that we that we are sending this qubit, and we immediately know on the other side. But you're not saying.
I'm not saying anything about sending any qubits at all.
No. Sending the information of this qubit in the state in which he was. But
That's
you're not
correct.
saying you're not using the quantum information. So we can basically.
We're just using the entanglement, right? All we're interested in is correlation.
But this is basically, we can check that we will see the state of this qubit in the same state that we were sending. But this means that we have one bit of information. But to establish this, we also need 2 bits, classical bits, that we need to send. So I don't see the purpose if we are not using the quantum information that we are sending. In that sense, we still need to send 2 bits, which
because you can send it all up. Because you can send it all up front. You send it at the beginning. So at the beginning, when everyone is bonded, you make sure they have enough entangled state. And now there's no need to do anything but measure.
I mean, we need to measure this on source and on target, right? And when we measure on the source, you're saying that we immediately measure this on source and package up.
Yeah, exactly. Right. So the point is that all the coordination happens at a bonding event, right? And we know that we have to do that anyway. You have to bond. So at bonding, you get enough material to go through you know, a certain number of decisions per epoch. And then go ahead.
I mean, is it like exchanging the random generator? So like sending sending a random generator at the bonding event, which will be telling others how exactly conflicts will be resolved in the future?
Something like that, yes. Very similar. Yeah.
Yeah, I have a question, like long-standing question. You were saying that Casper is about the conflict resolution part, but what about the other state? So in general, it's a state replication, right? So you have to know that each validator has exactly the same state even if there are no conflicts, you still need to verify that the state is the same.
Yes, that's correct. But the important thing is that you can separate out the state that's being transmitted from from the criteria for deciding the winner of the race.
So you sort of have two agreements. One is the winners of the race, and another is more like data checking of the data, if data is actually the same. So data replication.
That's correct. The data replication part is the business logic. It's the smart contract. Has nothing to do with the consensus, right?
But you need to,
the consensus. The consensus just said that as long as everyone gets the same data, then once you've selected the winners of the race, everyone will be in the same state. That's the way to think about it.
Yeah, but you still need to verify that in some way. So I'm just.
Yeah, you have to verify that everyone gets the same data, but that's different. That's a message validity protocol, as opposed.
No one cheated as well.
No, you don't care about the cheat, because the cheating is only in the winners of the race part. So as long as everyone gets the same data, so the double spin part of cheating you can protect against with the implementation of a cell, right? And the cell relies entirely on that everyone agrees on the winner of the race. You see what I'm saying?
Well, sort of. Can I say that I'm totally get that, but maybe once.
Yeah. Essentially, if you look at the cell implementation, right? As long if you have two copies that are separated in space of the cell, right? And so as long as they all agree on the winners of the race, if the data packets are identical, they must be in the same state. Do you agree?
Yeah, they must be, but what if someone just received something and cheated and pretended that it received something else? And this is what Casper, for me, like, you have to be sure that no one substituted something and said it's the same.
Yes, that's correct. That's correct. Yes. But again, that's the data integrity part of the protocol, as opposed to the race winner part of the protocol.
I see.
Right.
Okay.
Yeah. So that's kind of my point, is that you can separate those concerns, and you can get like dramatic speed ups as a result. Now, if we go back to the space calculus, now gives us a notion of location, right? So we can say that the sub entity, in this case a process, in the location, in the context, is the particle, right? So in particular, whatever we're putting in the pair, right? You can assign some observables that are associated with that location, and now we have a clear requirement, or a clear demand, and that demand is that no matter for any two pair of locations, the particles or the observables are entangled if they're correlated, right? If they're correlated according to the, you know, the requirements of quantum mechanics. So we can say crisply how we would have to modify the space calculus to get a notion of entanglement, right? So because now we have a notion of location, and we have to be able to get the correlations no matter how far apart they are, which means for any pair of locations, the copies have to give you the correlations across the observables in those locations. Does that make sense?
Can you explain? Do you think about space in a sense that this is the way how to achieve consensus, or consensus is something that is applied to state, moving processes to different states?
So, thank you for that question. I'm not approaching consensus yet. I'm simply saying, with the space calculus, we now have a notion of objects moving in space, so we can represent dynamical systems. But by the same token, what's also clear is that without some additional work inside that calculus, without some additional coding of some kind, we do not get the kind of correlations across locations, right? So without some protocol like Casper or something else, you won't. Like the only kind of observable we have is reduction, right? So for two copies of the same process in two distinct locations, we will not see correlations, right? So in particular, if I have a process that has a race in it in one location and a copy of that process with the same race in another location, I will not have a correlation. Information about how the left copy resolved the race does not tell you anything about how the right copy resolved the race. Does that make sense?
And the reason is because they are in some kind of conflict, right?
No. I'm just talking about just the space calculus that I presented 2 weeks ago, right? Or last week? I can't remember.
I think a correlation is something that I don't quite understand.
So the notion of correlation is that, like in the case of spin, if I measure the spin of two entangled particles, right, then the spin on the one, measuring the spin on the other, on the one, allows me to know with certainty the value of the spin on the other particle. If I measure the winner of the race in one location, does that tell me with certainty what the value of the winner of the race at the other location?
Oh, I see. Okay. And how
So-
we can achieve correlation?
Well, this was the point I was talking about before. If I have
Mhm.
Casper running between the two copies, that's one way to achieve it. Does that make sense?
Yes. Okay. Oh, I see that. I think that now I'm starting to understand.
Yeah.
So
So
mhm.
go ahead, please.
This process that is moving, you said this is the like a particle that we can somehow entangle with some other particle that is moving. So this
Yes.
is outside. This is outside of the rolling. This is why you're saying that this is part of consensus, right?
I don't understand your question. Can you ask it in a different way?
I'm thinking if we have two particles that we want to somehow correlate, we will not
Yes.
do this inside the rolling itself, or this will be like additional part that will correlate these two particles, right? Somehow.
Yes. So again, I'm just restricting my attention not to the space calculus, not to Rolang, right? So Rolang doesn't work on its face because it doesn't have a clear notion of location, right? So we'd have to work with Rolang a little bit. We'd have to tinker with it to have a clear notion of location that's related to observables, right? So in the space calculus, the thing that we've done is we've connected observables to locations. So the only observable you've got in these settings is a reduction. Your COM event is your observable. That's so that's all you've got to probe the system is the COM event. Go ahead.
Greg, I have a question. So is the concept of location in any way related to namespaces, or is this much more dynamic than namespaces?
It's exactly related to namespaces. So what we've done is to say that a location is a name, but remember that we started with an a priori definition of a location. So we said the idea of a zipper gives us a location in a data structure that satisfies, that the type constructor is differentiable, right? So in other words, a location is a pair, a one-hold context, and so if T is the type, we a location in a given instance of T is a pair, a one-hold context, and a sub T that fits into the context, such that when you fit the sub T into the context, you get the T. So just to at the risk of being boring, I'll repeat it. So if T is my data structure, an instance of some type curly T, then a location in T will be a pair, one hold context, which is the derivative of curly T, an instance of a derivative of curly T, and some T prime, such that when I apply the one hold context to T prime, I get back T. That's the notion of location that is given by the zipper. And so we can apply that to all kinds of data structures. So the thought is, well, we know that the row calculus is a data structure, right? All the processes are instances of the data type for the abstract syntax tree for the row calculus. And so now I can form locations. And now the tricky bit is, how do I make locations in that sense also be names in the sense of namespaces? And the space calculus solves that problem. It says, okay, now I've got names which are also locations in the sense described before. And so now I can have observables that are located in space. So that's the idea of the space calculus. And now the next trick is, so I can describe dynamical systems that way. I can now get things that are rich enough to model physical objects in space, moving in space. And so can I get these kind of quantum correlations of things moving in space? Because if we wanted to have an it from bit kind of arrangement, if I want physics to show up on top of this information theoretic substrate, the space calculus, then I would have to get these kind of quantum correlations. And so I'd have to see that, you know, an observable that I measure in one location, having made that measure, I know that there's an entanglement going on, or sorry, let me say it this a different way. If I have to be able to entangle states so that if I make a measurement at a location, then I know with certainty the outcome of a measurement for the entangled state at the other location. So if my system is of sufficient richness, you know, so my quantum space calculus is of sufficient richness, then I can model those kind of phenomena. Does that make sense now?
Yes, yes. So you're not saying what is the type T, right? This can be rolling with some additional stuff, but you're not saying anything right now. You're just saying that there is some type T that we can create a context and we can create location.
Yeah. So the beginning point is I have an abstract characterization of location.
Mm-hmm.
Right, it was given to me, and there's good reason to call it location, and that's, you know, that's the result of a bunch of work by very smart people, right? So we don't have to, you know, it's like if you doubt that, well, go take it up with the community and say, well, I don't think that's a good notion of location, right? And that's a reasonable discourse to have, but the point is that the community has kind of pounded on that notion of location, and it's fairly robust. And so we can say, all right, we're going to accept that as a notion of location. I mean, you could reject it, but if, you know, in order to go further in this argument, we say, okay, we're going to take that as a relatively robust notion of location. And now we're going to see, can I link that idea of location to an idea of observable? So I can have observables that are located, and that idea yields a domain equation, right? So in other words, I'm going to start with the notion of observable as COM event in the row calculus, and then so can I then make it so that COM events which happen at names correspond to COM events happening at locations, and that gives us a domain equation, and then the space calculus is a simple presentation of a solution to that domain equation. There are lots of other solutions, but the space calculus is kind of like, and in fact, I showed that there are several different versions, several different flavors of the space calculus, but all of them end up giving you a solution to the domain equation in the sense that you get reductions at locations. Does that make sense?
Yes, yes.
Cool. So since we have located observables, we can now ask for quantum correlations, right? So we can now ask for entanglement at locations, and then ask, well, how would I achieve that? And so the point I was trying to make is that there are two different ways to look at Casper, right? You can look at quantum information as a way to implement Casper, but you could go the other way, and you could say that Casper is like a classical simulation of quantum. Does that make sense?
Can you maybe
So
explain
you can
this
say,
more?
yeah. So think about it just abstractly, right? Just like there's in the real world, we could say, all right, I want to implement Casper, and one way I could do that is have the quantum information give me the winners of the race, and we can see roughly how that would go, right? I mean, that part is relatively straightforward. I mean, there may be lots of details, but in the, at the 20,000 foot level, we can say, yes, I see how if you handed out a bunch of entangled states, and if everyone consulted their end of the entangled state, then everyone would agree on the winners of the race, right? Does that make sense?
Yes.
Okay, great. So then, at least in terms of what Casper is supposed to do for our implementation of the row calculus, we can see how we could use this quantum information to give us the function that Casper is supposed to do for us. So I could just take that and turn it upside down. I could say, well, now suppose that I wanted to implement the kind of correlations that I see in quantum mechanics. And the only kind of observables that can be correlated are COM events. And so the only real observables are race conditions. So what could I do to get that kind of correlation? Well, I could use Casper. And then as long as, Casper didn't leak any information that was observable to the world in a way that, like quantum mechanics doesn't leak any information about the information flow, right? It's like you can't poke below quantum mechanics and say, see, there's a channel that you're using to get this to happen, right? The whole thing about the Bell experiments is there's no hidden variable, so you can't there's no channel-based communication that's making this happen. That's the non-locality part, right? It's just happening. And so if my implementation of Casper was airtight in the sense that it didn't leak any information about how it got the correlations to happen, then I could replace quantum mechanics with Casper to get the correlations. Does that make sense?
I think yes. I think yes. So Casper is basically simulating what quantum mechanics is
Yes,
doing.
exactly. Casper's
and
yes.
from the perspective of reductions, all of these correlations happens, and we don't know why, because this is part of what Casper is doing in some kind of like a background, right?
Exactly. That's the idea. Yes.
Thanks for explanation.
No. Thank you for all the questions. No, this is very helpful. It helps me explain and get the ideas across. And so the flip side of all the intuitions about using quantum information to implement consensus allows us to at least come up with a conceptual framework where we could take the space calculus and add something that's very Casper-like to get the quantum correlations. And then let me just check the time here. Yeah, okay, yeah. So I'll just make one more comment and then call it for today. So there is another way to do this, which is that you could create matrix-like things. So you could demand that the names, which are locations, also have a matrix-like structure. And we talked about several weeks ago how to encode matrix linear algebra operations in Rolang. So the other thing you could do is to enrich the location structure so that you have matrix-like operations. And then you could, because you have the matrix-like structure, you could also do the quantum mechanic thing, the realization of the quantum information in terms of that structure. Because this essentially, you know, entanglement is a consequence of linear algebra. It's is the long and short of it. And so if you want to mimic that behavior, if you have enough linear structure like that, then you can also implement that kind of non-local correlations. And so you could also code it up that way. It's a little bit mind-boggling to see how to do that, but that's the basic idea. So you can either simulate it, and as long as you don't have any information leakage from the simulation to the level up, you can get it done that way. Or you can, they can say that there is no mechanistic reduction. It's all in the magic of linear algebra, and you can get it done that way. Now, there may be other solutions, but those are the two solutions that I can see to get the quantum non-local communication of information happening in the space calculus setting. So anyway, hopefully that was food for thought. I know it certainly was very stimulating conversation for me, and I'll see many of you in the Dev Stand-Up. Thanks for your time and attention.
Thanks.
Yep, thank you.
Thanks.
Sure.